Here is a 2D particle equilibrium problem. So we have a continuous cable that goes from A all the way to C. So there's not a node here. It goes all the way straight through. And on this rope there is or on this cable, there's a pulley at B. And we have a force pulling on that pulley. Now that force is not pulling straight down, but it's pulling at an angle. And we know that it's pulling with a magnitude of a force of 5 kilonewton, but we don't know what the angle is that it's pulling at. But we do know what the angles are between the rope and kind of the horizontal here, or the cable and the horizontal. So we are now asked to find what the tension in the cable is, TAC. Remember that it's a continuous cable, so regardless on where we cut it, TAC is always going to be the same. And we're also looking for the angle theta. So to do that, we will start out with a free body diagram. We will define ourselves a coordinate system, X and Y. And then let's see, we will draw ourselves kind of more or less the node, and then we'll say we have two tensions, one in this direction, TAC, right, because it's that cable, and then we have another one in this direction, also TAC. Right, doesn't change. It's the same tension in that whole cable. And then we have our load, which is F going off in this direction. And what else do we know? We know that we have an angle here. That angle was 14 degrees. And then we have an angle here, which is 71 degrees. And we have an angle here, and that is theta. All right. So now we have our free body diagram. We can quickly think about if we have enough to solve this problem. Right? We have one unknown, which is TAC, and we have another unknown, which is theta. We have a two-dimensional problem, so we have two equations and two unknowns, which means we can solve this. So what we can do is we can write our equilibrium equations. We can start in the x direction. We can say sum of forces in the x direction equal to 0 and is equal to, now none of them is going straight in the x direction, right? They all have components in both the x and the y direction. So we could put them into their components, right? This would be the components of TAC in this direction. So this would be TAC x1, we'll call it, right? Because that component is going to be different on the two sides. And this would be TAC y1. And then over here, this would be TAC x2 and TAC y2, and of course the same with F, right? This would be F y and F x. So now we have everything in our x and y components. We want to look at x, then we can say, well, we have this component here going to the left, so it'll be negative minus TAC x1. On the other hand, we have it going to the positive direction, so that would be plus TAC x2. And then from F, we get just a little bit of a component there, but it's going to the right, so it's positive, plus Fx. All right. Now, how do we write this in terms of F and in terms of TAC? All right, so we can say this would be equal to minus TACx would be the adjacent leg, right? So it would be TAC times cosine of 14 degrees. And then plus, this is still the adjacent leg, so TAC times cosine of 71 degrees, right? So that's what we can see there. They're different. And then we have Fx. Now Fx is not the adjacent but the opposite, so that would be plus F times sine theta. All right, maybe we can rewrite this just slightly. Right, we can say that would be not F, but T. TAC times cosine 71 degrees. Oh, let's do it the other way. Yeah, let's flip it around so we can get rid of that negative sign. Let's move the two TACs to the other side. Right, so that would be positive then. So it would be cosine of 14 degrees minus, don't need the TAC, cosine of 71 degrees, and then we leave F on that side, so it's equal to F times sine theta. All right, that would be our equilibrium equation in the x direction. Now, unfortunately, we have both of our unknowns in this equation, so we can't solve it directly. So, but let's see if we look in the y direction, if we have more luck there. In the y direction, we would have TACY1 going upward, so positive. TACY1. We have the other component going upward too, so TACY2. And then we have minus FY because it's heading downwards. That means in this case, both of our TACs are the sines, so it would be TAC times sine of 14 degrees plus TAC times sine of 71 degrees. And then minus F times, this is now cosine because it's the adjacent leg, cosine theta. Again, we can rewrite this, bring this to two different sides. So we'd have TAC times sine 14 degrees plus sine 71 degrees, and we brought that to the other side, equal to F times cosine theta. Now again, we have TAC and we have theta in the same equation, so no direct solution too, but we now have our two equations with our two unknowns. So all we have to do is we have to solve those two, right? So system of two equations should be easy enough to do. I think the easiest to do is going to be to divide those equations by each other. So we can say TAC, let's do that one first, right? So TAC of cosine 14 degrees minus cosine 71 degrees divided by TAC of sine 14 degrees plus sine of 71 degrees is going to be equal to F times sine theta divided by F times cosine theta. Right, that's pretty straightforward. Now we can see, of course, that our F's cancel out, our TACs cancel out, so we're only left with theta. So we have one equation, one unknown. Now we know, of course, that sine over cosine is just tangent, so we can say that just right here maybe equal to tangent of theta. And if we then go in and say solve that for theta, then we can say theta is equal to inverse tangent of all of this. So cosine of 14 degrees minus cosine of 71 degrees. We don't need that bracket there. Divided by sine 14 degrees plus sine 71 degrees, and all of that, all that, then that gives us inverse tangent of 0.543, and that is 28.5 degrees. All right, that's what we get. So we now know theta. Once we know theta, we can just plug it into any of our equations to get TAC. Right, so we could, for instance, say, we have the one down here, right? So we said not F, but TAC. TAC, right, if we look up there, times sine 14 degrees plus sine 71 degrees is equal to F times cosine theta. If we want to have TAC, then we just have to divide by those two signs. So it would be F times cosine theta divided by sine 14 degrees plus sine 71 degrees. And that is equal to, what was our force, was 5 kilonewton. So it would be 5 times 10 to the 3 newton, because it was a kilonewton, times cosine of 28.5 degrees, or whatever accuracy our calculator gives us, divided by sine 14 degrees plus sine 71 degrees. And that gives me 3,700 Newton, which is 3.7 kilonewton. All right, so with that, we have found what the angle is and what the tension is in these cables if we have a force that's pulling like this and we get these specific angles.